Lakatos, Cellucci, and Heuristic Please go ahead.
So can you all see the screen now?
Yeah, we can see. No.
You can.
Not on the projector. I know. Oh.
Ah. Oh.
Well, it didn't matter. I think that's
Yeah, probably.
But not how. Yeah, no. It was working before.
Yeah, in the morning. Yeah.
I'm sorry. Huh?
No, because the speaker is supposed to. Maybe
Okay, so let's move on.
It's something to do with
it's something.
I can see it in the United States.
I know the online you can see it, and we can see it from the computer. But I think that from the room they can't see the project on the screen, on the common screen.
Yeah, so I think what you need to do is now to change the source on your side so that it projects what is on the screen to the projector. So there should be it should change the ports in the computer.
Yeah. Where? Sorry, Otávio. We're trying to solve the problem here.
Yeah.
That's okay.
Yes, we never, none of us uses mic. Salve, non riusciamo a proiettare lo schermo. Non c'è. Che non è questo, perché non ci sono le cose. Esatto, cioè questo qua è lo schermo sotto, perché ovviamente sta proiettando qualcuno da fuori. Vogliamo spegnere di accendere? Sì, ma forse dobbiamo pure. Forse pure quando si accende prima il PC e poi il connettore
Non abbiamo toccato nulla.
E poi non si bravo.
Dobbiamo fare la pausa. Questo bisogna di qualche secondo. Ah,
Vediamo. Vediamo
no.
di solito è buono, il gatto.
No, no, potrebbe comunque. Vabbè, niente, metto il mio computer qua davanti, vediamo più. No,
È tutto collegato? Sembra di sì. Sì, ovviamente. The projectors, no? Yeah, we're trying to change the source, but it's not working.
Move on, yes.
Lo so, dovete cambiare.
No,
mi dispiace. Con la tua? Il fatto del collegamento. Mi dispiace, volete cambiare anche? Okay. Maybe you can, yeah. Someone can come here, yeah. There are two screens, so, okay. It's okay, it's okay. Okay, Ottavio, you can start. You can start with, we can see it in one way or another.
Yeah,
I consider. Okay, I consider that the new time.
okay.
Okay, go ahead.
All right. Well, first of all, I'd like to thank the invitation to be part of this great celebration for Carlo's work. It's a pity that I'm unable to be there in person with all of you in Italy. That would be much nicer. But we'll have to wait for another occasion. So what I'm going to be doing today is it's actually, I think there's far more agreement between the way I think about heuristic philosophy of mathematics than disagreement relatively to what Carlo has done. So in many ways, I think I'm going to raise a small quibble, right, about a certain way of thinking about heuristic philosophy of mathematics. And of course, Carlo started with Lakatos as a sort of the regional formulation of the heuristic view. And then he adds, an inductive element to it that I would like to offer some pushback on, and then see what we get as a result. So, so the heuristic philosophy of mathematics, I think, emphasizes the importance of problem solving to make sense of mathematical practice, right? And within that, the analytic method is contrasted with theorem proving using the axiomatic approach. That's something that Carlo in his book the making of mathematics, it develops in great detail, right? And in developing the heuristic view, Carlo juxtaposed Lakatos' original formulation, right, of the view with his own considered inductivist version of the overall approach. He criticizes then Lakatos' view for being ultimately unable to offer a proper heuristic, right? And that's very unfortunate, right? Given that the whole point, in many ways, of Lakatos was indeed to make sense of the role of heuristic considerations, especially in the case of mathematics. So what I'm going to do in this talk is to respond to Carlo's challenge. And we're going to articulate a kind of Lakatosian deductivist version of the heuristic view that I think will allows for a proper recognition of the nature and role of heuristics in mathematical practice in the way that I think Lakatos intended it to go through, right? I think there are important shifts when Lakatos shift from philosophy of mathematics to the philosophy of the natural sciences. I think he could have done actually a better job integrating the two views than he did in the end, but that will be a topic for another day. So what in the end, my suggestion is that I think we should adopt a more pluralist view about the heuristic view, right, which tracks different orientations within mathematics. So ultimately, I think there could be a version of it that is deductivist. I think that's the Lakatos' intention, and an inductivist in the way that Carlo suggests. I think there are some advantages to the deductivist view, and that's what I'll try to suggest today. So let's start then by highlighting the central features of the heuristic philosophy of mathematics. So in the way that Carlos has it, he highlights very clearly three key assumptions. So the first one, the mathematical problems are solved by the analytic method. Therefore, mathematics is problem solving by that method. Second, solutions to mathematical problems are never certain, but only plausible. Indeed, mathematics is part of human knowledge, and human knowledge is never certain, but only plausible. This is actually the second feature, is something that also derives straight from Polya, right? And especially in his work on mathematics and plausible reasoning, which tend to highlight exactly the fallibility of mathematical knowledge claims. And thirdly, that there is no part of mathematics such that all of other parts of mathematics can be reduced to. Specifically, there's no mathematical theory such that all other mathematical theories can be reduced to it. Mathematics consists of a variety of mathematical theories related in multiple ways, right? And then, so there's no, in effect, it's part of the heuristic view that you don't have a kind of a set theoretic foundational picture as being basic, right? And every piece of mathematics should be explored and formulated in its terms. Now, I think these three significant features are really important, right? So let me say a little bit about each one of them. So on the analytic method, right, the idea that mathematics is a problem-solving activity. What exactly is that analytic method? Of course, the bulk of the book, of Carlo's book, develops that in great detail. So in a snapshot, the idea would be that we start from problems, we formulate hypotheses for their solution by non-deductive inferences, right? That's where the inductivist bit comes in, and establish the plausibility of hypotheses through a comparison with experience, right? And that's, again, where the fallibility will work out, right? Now, that fallibility is central to what mathematical knowledge ends up being, right? There's no certainty in mathematics. At best, we get plausibility. And then the third feature, the anti-reductionism, right? The mathematics is ultimately anti-reductionist. That includes set theoretic reductionism. So there is no fundamental mathematical theory. In part, that's important because there's a sense in which having this foundational picture goes against, in some instances, with a plasticity of mathematical practice, right? It forces things to be cast in a specific limited framework. In some cases, this might actually be heuristic fruitful, but you shouldn't take that to be a requirement across the board. So I think that these are important traits of both mathematical practice and the heuristic view, right? And then I think there's very little doubt that mathematics is indeed a problem-solving, fallible activity, right? And there's, I think, serious concerns about reductive projects in mathematics, including set theoretic ones, despite their usefulness. So in these broad strokes, I'm largely in agreement with what Carlo has to say, right? My point here, however, is that I think there are different ways in which these broad strokes can be worked out in detail, right? And so here I'm going to try to contrast two different views or two different ways of articulating the heuristic view, right? Carlos and the kind of Lakatosian inspired view that I would like to offer as a contrast, right? So with regard to the first feature, right? The analytic method can indeed be characterized inductively, right? That's Carlos' preference. Or it can be characterized purely deductively. And I think that's what Lakatos would prefer to go. I think in that point, when he was writing proofs and refutations, he was a sort of a hardcore Popperian, and that showed, right? The second feature, right? The mathematical knowledge is fallible and not certain, right? We can highlight that in the way Carlos does, or we can understand it slightly different ways, right? The mathematics is actually not in the business of providing knowledge, but actually in the business of solving problems based on strong, although not conclusive evidence, since concepts can always be revised and refined. And I think that's something that Lakatos emphasizes, right? The importance of concept revision. That brings in an element of fallibility, right? And we can, resist talking about fallible knowledge per se, right? So I'm going to say a few things, a few points about, the component 2 and 3. The bulk of my talk will be on 1, right? So let's just say, one point about how the contrast that I see here with Carlos would go, right? So, for example, I think part of the, talking about fallible knowledge, though odd, right? If I say, I know that not every topological space is a metric space, but I may be wrong about that, right? That's something odd in saying that thing, right? So you say, well, if you know that, how can you be wrong about it? So the response would be, if it turns out that what you thought you knew is mistaken, well, then you didn't know. You just thought you knew, right? So I think part of the issue here is how to reconcile the facticity of knowledge claims with the fallibility, right? And that's a problem, of course, it's a larger problem in epistemology. Contextualists try to tell a story about how this could be worked out, considering different contexts and different standards of knowledge. My suggestion would be, well, maybe we don't talk about knowledge at all, right? We talk about evidence, right? And realize that the evidence is often not conclusive. And that gives, in the case of mathematics, in part because of conceptual shifts. And that allows us then to talk about fallibility, leaving the notion of knowledge behind. Of course, there's far more to be said about that, but that's what I'll say about this for question of time. Let me say a few things about the third point, right? So, as Carlos points out, mathematics is anti-reductionist, since there is no fundamental theory, right? Well, there's a slightly stronger version of this view. Not only that mathematics is anti-reductionist, but it cannot be reductionist at all, in the sense that there cannot be a reductionist theory, a fundamental theory that captures the entire body of mathematics without distorting seriously its content, right? And that's another way in which this third component can be worked out in a sort of more robust and stronger form, right? So think about, the set theoretic reductions of number theory. There's a sense in which number theory is about numbers, not about sets, right? No matter how useful the set theoretic representation of natural numbers may turn out to be, right? So there is a sense in which you're changing the subject matter, right? If you're doing arithmetic in set theory, well, you're not really doing arithmetic at that point. You're just doing a little, version, impoverished version of number theory within set theory, right? Also, consider doing graph theory in set theory alone, right? Without ever drawing any graphs, since there are no drawings in set theory, right? Well, I would say good luck with that, right? So there is a sense in which even thinking about, or probably, arguably, the most thorough foundation, even there are serious concerns about distortion of the subject matter. And one may perhaps can take a stronger stance and say, well, there cannot be a proper fundamental theory, not only that there isn't one. Now, it's possible that Carlo would be happy to embrace this stronger form of anti-reductionism, right? I'll leave that as just another alternative, right? So having said a little bit about 2 and 3, now what I'm going to do for the rest of the talk is focusing on 1 for due to time constraints, right? The inductivist, deductivist bit, right? Carlos raises a number of objections to the formulation that Lakatos provided of the heuristic view. So let me address those, and the inductivist, deductivist bit would emerge as a result, right? So I think one of the most stronger concerns that Carlo raises is that Lakatos, in the end, fails to account for how we can arrive at a naive conjecture. So much about talking how we can get to discover new hypotheses and new conjectures. And in the end, on his view, Lakatos really doesn't have a proper account of that. Why? Here's his point. Lakatos says that the first step of the method of proof and refutations is that naive conjecture, because discovery moves from the naive conjecture, right? So then one would expect that the first rule of Lakatos' method of proof and refutations would indicate how to arrive at the naive conjecture. But the rule does nothing of the kind. For it states, and here it's Lakatos, rule 1, if you have a conjecture, set out to prove it and to refute it. Inspect the proof carefully to prepare a list of non-trivial lemmas, proof analysis, find counterexamples, both to the conjecture, global counterexamples, and to the suspect lemmas, local counterexamples. So the rule assumes that you already have a conjecture. Therefore, Lakatos' method of proof and refutation does not account for how to arrive at the naive conjecture. So he may, in other words, he fails to account how we can ultimately come up with or discover new hypotheses. Now, strictly speaking, I think the rule involves just a condition, right? If you have a conjecture, set out to prove it and refute it. Of course, the rule does not assume that a conjecture is readily available, right? The rule has nothing to say if no naive conjecture is on offer, right? Modus ponens does not apply without ascertaining the antecedent. So we do need to have the antecedent before we can even apply, right? Apply the rule. The question, however, is does Lakatos have enough to say about how to generate these naive conjecture? And I think he does, right? In fact, his significant point is that through careful, thorough, systematic conceptual work with no inductive inference in the background, we can generate such hypotheses. And part of my responses here will be to see how this will be worked out. Now, as we know in proofs and refutations, Lakatos explores in detail Euler's conjecture about the classification of polyhedra in terms of their number of vertices, edges, and faces, right? That satisfy this equation, that the number of vertices minus the number of edges plus faces equals 2, right? So Euler considers this conjecture and declares, Carlos quotes here from Euler, from the consideration of many types of solids, Euler says, I have been led to understand that the properties which I had discerned in them clearly extended to all solids, even if it was not allowed to show this by rigorous demonstration. Thus, Carlos says, Euler states that he arrived at his conjecture by induction from observed cases. So he was considering various cases of polyhedron. He noticed that they all satisfied this conjecture, and so he inductively generalized to all of them. Of course, this is not a proof, and he acknowledged that it was not a proof. Now, on the surface, I think this is a reasonable inductivist reading of Euler, right? But I don't think that the passage here needs to be interpreted in this way. And I think there is another way of interpreting it. And I suggest that that's the way in which a Lakatosian would actually read Euler's description, right? Consider instead the concept of a polyhedron, right? And interpret Euler as operating an application of this concept to a variety of types of polyhedron, right? Not to particular cases, but rather to generic kinds, right? Thus determine that certain properties regarding vertices, edges, and faces of polyhedra, which have been identified in these objects, extend to all solids of these types, right? So when you're doing that, you're doing a little bit of conceptual application, right? So Euler is actually formulating a hypothesis. He's formulating a naive conjecture to the effect that all polyhedra have the relevant properties regarding vertices, edges, and faces, right? Rather than inferring them inductively, the hypothesis from particular case. So rather than, of course, this is a familiar move, right, in the Popperian corpus, right? Rather than thinking that you're actually giving evidence to a hypothesis by considering particular cases and inductively inferring them, consider that what you're doing is simply making up a hypothesis, right? You're testing it. And we're going to see in a minute how you can come up with that hypothesis, right? By examining the concept of a polyhedron. And I think that's what ultimately Euler actually did, rather than an inductive inference. Indeed, as Lakatos points out, and Carlos quotes these passages, there are no such things as inductive conjectures, right? One finds, Lakatos says, no inductive starting point at all in this process. So it's not part of the proofs or refutations approach to have this kind of inductive leaning. After all, naive conjectures are not inductive conjectures. We arrive at them by trial and error. Right? The idea, trial and error as a way of generating hypotheses. Now, here comes then Carlos' second objection. Well, it turns out that trial and error are just induction in ship's clothing, right? So you relying on those inductive procedures when you through your process of trial and error, right? He tells us, Popper himself says that the success of trials depends very largely on the number and variety of trials. The more we try, the more likely it is that one of our attempts will be successful. This amounts to admitting that trial and error depends on induction. Then it's contradictory to claim, as Lakatos does, that naive conjectures are not inductive conjectures. We arrive at them by trial and error. I would like to resist that, right? I think it's not clear to me that Popper is actually being incoherent. After all, being successful at a trial is not to inductively infer the hypothesis from particular cases. That would be indeed incoherent with what Popper intends to do. But rather, what's the success there is to come up with a hypothesis that once tested is not immediately refuted. So it's a different level of success, right? So, and it's interesting, Lakatos himself raised that objection to Popper, right? At some point, he called a whiff of inductivism with his notion of corroboration and so on. And I think, strictly speaking, Popper did not go that far, right? The idea is that the idea of success, right, in trial of error is not to lend some sort of support from particular cases to a general conclusion, right? But just to come up with a hypothesis that you can then test. That's the success, right? Hopefully a hypothesis that's not just ruled out, in the very first test that you came up with, right? And hence the idea of corroboration. So far, the hypothesis has not been refuted. I think that's all that Popper really needs here. That's all that Lakatos really needs, right? And in fact, exactly the same point, I think, would apply to Euler's conjecture that we talked about a minute ago, right? Lakatos says, these trials and errors are beautifully reconstructed by Pauli. The first conjecture is that the number of faces increases with the number of vertices. You just consider that, right? And immediately this is refuted. So, okay, that's not a good hypothesis, right? You come up with another one then, right? The number of edges increases with the number of faces. The number of edges increases with the number of vertices, right? Again, those turn out to be refuted, right? And you come up with a fourth, winning one, right? Oh, it's not that we need a little more. We need the sum of the number of faces and the sum of the number of edges, right? Would increase, vertices would increase with the number of edges. It's a little more complicated. Note how you can get to the more complicated hypothesis by considering the concept of a polyhedron. What are the crucial features of that concept? Well, relations among vertices, edges, faces, right? So it's by considering the concept of polyhedron, exploring relations among the components of that concept, the hypotheses get formed by trial and error in this way. Noted that there is no inductive here. We're just trying things out, right? And trying to figure out if some hypothesis is not straight out refuted by the evidence, right? So there is no need here to adopt an inductivist methodology to generate a naive conjecture. The conjecture is a result of application of a concept to various types of objects and the identification of a generic pattern. The generic pattern emerges exactly as a result of this give and take, right, of refuting these conjectures, right, given the evidence, right? So try and error need not, in fact, should not be thought as involving inductive inferences. It need not involve inferences at all, right? But rather conceptual analysis, critical examination of types of objects, and the identification of common patterns, right? Now, central here are concepts, right? In many ways, I think the most important lasting contribution of proofs and refutations is exactly a study about concepts and concept shifts in mathematical practice. It's by focusing on the concepts, their study and application, rather than inductive inferences, that we understand this process of how new hypotheses are formulated in mathematical practice. Now, of course, the deductive inferences would eventually be involved, and they are involved in the refutation of these pre-naive conjectures, right? The pre-naive conjectures are those that didn't quite raise to the point of a naive conjecture yet, because they just have been ruled out immediately, right, by the data. Like the number of faces increases directly with the number of vertices. Very immediately, you have counterexamples to those things, right? Those are pre-naive conjectures, right? So deductive inferences will come in, right, by exhibiting inconsistencies between the proposed conjectures and the application of the relevant concepts. That's the give and take of how to formulate, eventually formulate a naive conjecture through a process of pre-naive conjectures, right? And what we have the quotation there from Lakatos based on Pauli illustrates how those pre-naive conjectures eventually led to the Euler naive conjecture. Okay, here's what Lakatos said then. Mathematical heuristics is very like scientific heuristic, not because both are inductive, but because both are characterized by conjectures, proofs, and refutations. So what Lakatos is interestingly distinguishing here are two processes, right? We have a process of conjectures and refutations. That's where pre-naive conjectures are involved, right? That's the business of just straight out refuting some hypothesis just out of the available evidence. Until you reach the stage where you have a naive conjecture. When that happens, you start the process of proofs and refutations rather than conjectures and refutations, right? Because then once you have that, a naive conjecture, a proof then can be offered, right? You try to prove and refute the conjecture at the same time, right? And that leads to a process of careful proof analysis, by thought experimentation, lemma reformulation. So you reformulate the lemmas that may be violated in the proof, or you may reformulate the entire some of the assumptions of the conjecture as a whole. The result is an improved conjecture. And as we all know, right, and that's one of the central points of Lakatos proofs and refutations, proofs ultimately do not prove, they improve naive conjectures. And in that sense, we can already see a way in which knowledge is not, it is, the idea of fallible knowledge is put on a side in a way, right? What matters here are the sort of evidence, fallible evidence that we have. That's all proofs, that's the best they offer, right? They improve the naive conjectures. So we get a better hypothesis to make sense of the available evidence. Now, Lakatos continues, our naive conjecture was not the first conjecture ever suggested by hard, non-conjectural facts. It was preceded by many pre-naive conjectures and refutations. Right? That's the point about going back and forth with the counter evidence. So the logic of conjectures and refutations has no starting point, right? But the logic of proofs and refutations has. You start with the naive conjecture, followed by a thought experiment. So we start with these pre-naive conjectures that are, most of them are immediately refuted, right? And then until we can identify by making more complex, identify more complex patterns, until you get something that is not immediately refuted. And then we have a naive conjecture. Once you get that point, we can then try to prove and refute it and see. And then that's where we have something a little more stable that is open then to the process of proofs and refutations, right? So identifying pre-naive conjecture is the result of careful examination of applications of the relevant concepts to a variety of different kinds of objects. That's where current examples will come in, right? And no inductive inferences is needed in that process, right? Prior and error periods of conjecture and refutation should be overcome promptly, right? As Lakatos says, the main thing is to get out of the trial and error period as soon as possible, to proceed quickly to thought experiments without having too much inductive respect for facts, right? So the thought experiments here that he has in mind is what eventually is going to lead to a proof analysis once you're able to come up with a proof of the result. Interestingly, respect for employment of inductive inferences on Lakatos' view, in fact, damages scientific and mathematical development, right? So we should indeed, we have reasons on his view to avoid using inductive inferences. Why? Here's what he has to say. Such respect, right, for an inductive inference may hamper the growth of knowledge. Imagine that you arrive by trial and error to the conjecture that number of vertices minus edges plus number of faces equals 2 for the Raven polyhedron, and that it's immediately refuted by observation that V minus Z plus F equals 0 for a particular kind picture frame. If you have too much respect for facts, you basically go back to the drawing board, right? Especially when they refute your conjectures, you then go on with a pre-naive trial and error and look for another conjecture. You just, so that was a bad conjecture. Let's, dash it, right? But if you have a better heuristic, you at least try to ignore the adverse observational test and try a test by thought experiment, like Cauchy's proof. So here's what's going on. And Lakatos was very impressed by Newton, right? When Newton dealt with attempt refutations of his account by saying, sorry, the problem is not with the theory, the problem with the collection of the data and the analysis of the data, right? So Lakatos is saying, well, I mean, if you have a good heuristic, you should be able to turn apparently falsifying hypotheses into something that square code confirms the hypothesis, right? And that's exactly what this business about the Cauchy proofs has in mind. So you start with a conjecture, right? The V minus E plus F equals 2, and then you start simplifying it and say, okay, what if I start getting rid of faces, right? Then I will end up with a triangle that rather than refuting the view would actually confirm. So it's a really interesting thought, right? So you may actually turn what apparently may be a counterexample into something that supports the hypothesis ahead, right? So rather than rely on facts, one can improve a conjecture by refining the concepts initially introduced in the naive conjecture. Concept stretching then becomes the key component of scientific and mathematical development. And the rest of proof and refutations is an exercise in exactly understanding how this process of concept stretching will be worked out, right? So let me say a few things about that beyond what Lakatos has actually done, right? Because I think he was onto something very important with this business of concept stretching, right? Because a form of concept stretching, I think, also is implicitly involved, even in the period of trial and error, when we have a pre-naive conjecture, right? Since concepts are already used in this period, and they are applied to objects to generate refutations and counterexamples, right? But more broadly, when you have a naive conjecture, right? I think the crucial contribution of the dynamics of proofs and refutations is the conceptual innovation that emerges from those counterexamples. And it's a reflection of that conceptual innovation, I think, that is at the heart of what having a good heuristic is all about. So concepts are here stretched to accommodate possibilities that were not recognized prior to the counterexamples. I think that's the important insight that Lakatos gave us in proofs and refutations. And it's an insight that goes beyond the example that he worked in detail in the book with the Euler conjecture. So let me try to illustrate other cases. Given the limitations of time, only I'm going to give a number of examples in logic to illustrate how that will go, right? So I think Lakatos' suggestive metaphor of concept stretching can be understood in modalist terms, right? In the sense, a modalist is someone who takes modalities being primitive. You not explain what is possible or necessary in terms of possible worlds or things like that, right? The idea is that revised concepts in light of counterexamples express unacknowledged possibilities, possibilities whose recognition was precluded by previously inadequate, limited concepts, right? That's the point of where Lakatos says you need to have a good heuristics, right? A good heuristics would allow it exactly to realize, hey, the phenomena we're dealing with is actually richer than we thought. And that's what the counterexamples can, when properly dealt with, can help us understand, right? So for example, we're studying sets, right? And we run into Russell's set, right? The set of all known self-member sets, right? Of course, then we say, well, there's no such set, right? And that's the whole point of classical set theories, is to say, well, let's avoid this object, right? Because there is none there, nothing to be studied. Of course, in classical logic, it would be trivial to try to study some object like that, right? It's impossible to do that, right? However, it's perfectly possible to study an object like that if you change the underlying logic to a paraconsistent one, right? And you distinguish inconsistency and triviality, right? So, which classical logic simply identifies. So this is a possibility that classical logic forecloses, right? The possibility of studying inconsistent but non-trivial objects, like the Russell set, right? And in fact, in paraconsistent set theories, it's a perfectly well-behaved object, even though it's an inconsistent one. It has some properties, it lacks others, and it's an interesting object to study, right? So you can do that if you stretch the concept a little further than what classical logic and classical set theories would allow us to do, right? Second example, right? You may study quantum particles, right? And then on some formulations of quantum mechanics, Schrödinger file and others, it doesn't even make sense to talk about the identity of these particles, because nothing in the quantum mechanical formalism allows us to distinguish, say, an electron from another electron, right? We swap them around, and the quantum states that they are in remains the same. So, as Weil said, there is no alibi for an electron, right? Mike or Ike, who knows who is who, right? But interestingly, you cannot express that again in a classical set theory, right? Because given extensionality, two sets are the same provided that they have the same members. So the identity of the members of the set is presupposed as a requirement for it to form a set. So you cannot talk about objects that do not have identity conditions and put them in a set, right? So what do? It's to explore a possibility, right? And that's what quasi-set theories do. They restrict the principle of extensionality and say, well, only indistinguishable particles are required, not their identity. So you introduce rather than talk about extensionality in terms of the identity of the sets, you just consider the indistinguishability of their quasi-sets. So their members are indistinguishable. And of course, that's exactly what electrons are, right? Two electrons are indistinguishable from one another, given the quantum mechanical descriptions of them. So that's a possibility that can be studied. The concept can be stretched so that we can then not foreclose a possibility that was ruled out. Third example, the study of constructive features of mathematical reasoning. This is technically possible only if mathematical objects are not assumed to have certain properties just because of their completeness. That is, it's not assumed that they either have or not a property in question, right? A construction exhibiting the relevant properties needs to be obtained. So what you need here, of course, to do that is a constructive logic, right? So here, conceptual innovations emerge from the recognition of counterexamples, respectively, to the principle of explosion, extensionality, and excluded middle, right? So the entire process, of course, is conducted entirely deductively. Of course, Carlos disagrees, right? He would say, well, to make a deduction, you need premises. He's right about that. And premises are not discovered by deduction, but only by non-deductive inferences. Therefore, deductive logic is not the only logic that we have or need. Now, that's the point that I want to resist, right? Because arguably, the central concept of logic is that of logical consequence. What follows from what? Is a way we can formulate them. So an argument is then logically valid if the conjunction of the premises and the negation of the conclusion is not possible, right? That's a modalist formulation. Note that we understand consequence as a modal notion, right? Not in terms of model theory, right? A model theoretic formulation in set theory of consequence is already, I think, an artifact. And it has all kinds of artifacts, right? Because of the limitations of set theory. For example, the domain, ideally you want to say, well, the domain of all, the domain of set theory, when you apply logical consequence relation to it, should be the set of all sets, right? But in a classical set theory, there is no such set. Right? So you cannot even apply the notion of logical consequence properly in that sense, right? Not if you're, adopting a modalist version, you're not tied to that. And that's where, the anti-reductionist bit about let's think about set as the foundational picture also comes handy. Now, since inductive inferences are not logically valid, there's no inconsistency in the conjunction of premises and the negation of the conclusion in an inductive argument. I want to say that they are not really part of logic, right? Inductive inferences. They're doing something else altogether because the crucial notion of validity is not satisfied, right, by inductive logic. Also, given that via conceptual stretching in the way that we discussed with examples so far, why the concept stretching, concept application and trial and error, naive conjectures can be formulated deductively. And once they are formulated in this way, proof analysis can proceed also deductively. A purely deductivist, Lakatosian heuristic philosophy of mathematics, can be articulated. So we can actually take seriously on Lakatos' call. That was the editor's choice, but there you go. No, the logic of mathematical discovery, right? As what emerged from proofs and refutations. I think there is, in a way, a logical mathematical discovery, but the central feature there is a reflection of concepts and concept stretching that can be done purely deductively. All right, to conclude, I think Carlo has rightly identified the three central components of the heuristic view, right? I think I fully agree with him, right? Mathematics is indeed a problem-solving activity, uses the analytic method. Fallibility, right? Mathematics is fallible. Mathematical knowledge is not certain, right? At best, the knowledge is plausible. And anti-reductionism, mathematics is anti-reductionist since there's no fundamental, especially theoretic mathematical framework underlying the practice. So the spirit behind this version of the formulation of the heuristic view, I'm fully on board, right? What I suggest instead is a different way of interpreting the three conditions, right? Through a thoroughly deductivist formulation of the heuristic view, which I think is what Lakatos actually had in mind. And as I suggest, I think that can actually be defended, right? Especially, so that requires understanding the analytic method in a way that doesn't build in inductivist reasoning as part of it. That's the way I'm interpreting the analytic method. Right? Then with regard to the other two components, the view is able to accommodate the articulation of naive conjectures purely deductively. It's also so thoroughly fallibilist, the knowledge becomes secondary to evidence, right? So mathematics is a process of evidence gathering through proof analysis, right? So it's not a matter of knowledge, style is offering fallible knowledge and then trying to make sense what that means, right? But acquiring proper evidence. And the evidence is always fallible. And it's also the practice so strongly anti-reductionist that even theoretic reductions are seen as distorting the proper content of mathematical theories, whether when we're doing, say, number theory, or when we're just doing formulations of logical consequence, right? I think the result is then a form of pluralism about the heuristic view, right? You may be, deductivist, you may be inductivist, you may be hardcore anti-reductionist, that it's not possible to offer a fundamental mathematical theory, or you may be, more easygoing, that such reduction does not emerge, right? You might be fallibilist and have a concept of mathematical knowledge that is fallible, or do without the notion of knowledge and rather focus on the notion of evidence and how it is fallible after all. I would say, given the plurality of possible formulations of the heuristic view, the view is actually in very good shape. And I would say the more, the merrier. Thank you very much.
Time for Ciao Carlo. It is time for a few questions. So